In this video, we're going to talk about transactions and instructions on Solana. These are the basic steps to build a transaction. Effectively, we need to first create the instructions we want to invoke, where instructions are just some functions that exist on an on-chain account that we're trying to call. Once we have our instructions, we create what's called a message that includes our instructions. Taking this message, we then build our transaction, which is made up of the message and the signatures of each account that must be included as a signer for the instructions we're trying to invoke. Once we have a signed transaction, then we can go ahead and send that transaction to be processed by the network. So effectively, you can think of transactions as envelopes, and each instruction as an individual form that we fill out and put into our envelopes. First, let's look at the instruction type. Whenever we want to build and invoke an instruction, we have to provide three pieces of information. We have to specify the program ID, the accounts required by the instruction, and some instruction data. So the program ID is the on-chain address of the program we're invoking, which includes the business logic of the instruction we're trying to invoke. So the function we're calling, which is the instruction, lives on some on-chain account. So we have to specify what that program account is as the program ID. Next, we have to specify upfront all the accounts that the instruction requires. So this requires us to pass in a vector of what are called account metas. We'll go over this account type next, but effectively, we have to specify upfront all the accounts that the instruction either reads from or writes to. Lastly, we have to pass in some instruction data, which is an arbitrary vector of bytes. And this instruction data is generally used in two ways. First, it's used to specify the exact instruction we're invoking on the program, because a program might include multiple instructions, and it's used as a way to pass in any function arguments required by the specific instruction we're calling. For example, we could have a buffer, and the first few bytes is reserved to identify the instruction we're trying to invoke, and the remaining bytes are just the function arguments of the instruction we're calling converted into bytes, but it's all part of the same instruction data buffer here. Next, let's talk about the account meta type. So what exactly is this? It means in addition to specifying the address of each account required by the instruction, we also need to specify whether the account is required as a signer on the transaction and whether the account is writable, meaning if we're going to be updating the data on that account in the instruction we're invoking. So to use this account meta type, we would call account meta new if we want to create, or if we want to say the account is writable. And if it's a read-only account, we would use account meta read-only, which would mark this is writable flag as false. Next, let's talk about the transaction message type. So you can think of the message as a way to package up all the instructions we're invoking and add some extra metadata. So the first part of the message is the message header, which is just 3 bytes used to identify which accounts require signatures, which accounts are read-only, which accounts are write-only, etc. The second field is the account keys. So every account address for all the instructions are converted into an array that's included in this account keys vector here. The recent block hash is used to timestamp the transaction message, and our instructions are converted into a vector of what are called compiled instructions. We can take a look at the compiled instruction type here to see that the program ID is now indexed or referenced by index. The accounts are also referenced by index, and the account data is still the vector of account data bytes. So effectively, the instructions in the compiled instructions here, instead of listing each address, now point to the account keys vector here. And the message header is 3 bytes that specifies the following information: the number of required signatures, the number of read-only signed accounts, the number of read-only unsigned accounts. And this information is used to identify which account keys in this vector correspond to what type of account. Next, let's talk about the transaction type. So on Solana, transactions are made up of a message and some signatures that were generated by signing the message on the transaction. The number of signatures must equal the number of required signatures specified in the message's message header. What does that mean? It means in our transaction message, we have our message header and we have a vector of public keys. So these are all the account addresses that are required for all the instructions on our transaction. In the message header, the first byte specifies the number of required signatures. So that means whatever the number of required signatures is specified in the message header, that is the number of signatures we require and will correspond to the first account listed in this public keys vector here, which means the corresponding private keys for said public keys must be used to sign the message to generate the signatures we must include as part of our transaction. Next, let's use a basic SOL transfer as an example. So here in our main function, we connect to our local test validator, generate two key pairs that we're calling sender and receiver, and then build an instruction to invoke the transfer instruction on the system program, add that instruction to a message, add that message to a transaction, and send that transaction. At each step, we're going to log the instruction, the message, and transaction to see what we get. So if we were to run this example, we would first get our link to Solana Explorer, where we can see that we're invoking the transfer instruction on the system program where we have some sender, some recipient, and the amount of SOL we're transferring. If we were to inspect the logs, we would see the following. Here we have our from and to address here. We have our instruction, which has our program ID that we're invoking, the system program, each account required by the instruction as account metas. So we have our sender and our receiver, or the to and from key. The sender must be a signer on the transaction, and both accounts must be writable because we're going to be modifying the LAN port balance on the two accounts. And here is the instruction data buffer that identifies that we're invoking the transfer instruction on the system program and the amount of LAN ports we're transferring. So that would be here and split down here. So first 4 bytes identifies the instruction we're invoking, remaining 8 bytes, that's the LAN ports we're transferring. Then for the transaction message, we have our message header that says how many accounts are required as signers. So 1, that means this first key here must be a signer on the transaction and must sign the transaction message with the corresponding private keys. We have 0 read-only signed accounts, and then we have 1 read-only unsigned account, which is going to be this address right here, which is our recipient. And here we have the 3 account keys required by the instructions on our transaction, which, if you notice, also includes the program ID. We also have our recent block hash to act as a timestamp for this transaction. In this case, we haven't set it yet. And then we have our instructions in the format of compiled instructions, where instead of listing each address, we reference the account keys by index. So the program ID is at index 2 here, and then the from and to key are at index 0 and 1 here. And then we have the same instruction data buffer here. Now, once we add our message to a transaction and we sign it, we now have our signatures. So this signature here is generated by taking our transaction message and signing it with the corresponding private keys of the sender. And within our message, we now also have a block hash that's set that acts as a timestamp for said transaction. So once we have our transaction with our signatures and all the data that we need, with the block hash included to timestamp the transaction, we can go ahead and send that transaction. And what we get back is the transaction signature, which is actually just the signature of the transaction fee payer on the transaction. And that is what we use to locate the corresponding data for this transaction. Next, let's take a look at how this instruction is built. So for the transfer instruction, we're simply calling this transfer helper function, passing in the from key, the to key, and the amount of LAN ports we're trying to transfer, and it will return to us the instruction we're trying to invoke. Now, under the hood, this transfer function is functionally equivalent to the following code here, where we manually build the instruction calling new with bytes, passing in the program ID, the accounts, and the data required by the instruction. So for the transfer instruction specifically, the program ID is the system program because that's the program we're invoking. The accounts are simply the sender and recipient, and we need to provide these accounts as account metas. And since both accounts are writable, we're calling account meta new for both. For the sender, we're passing in true because we require that the sender is a signer on the transaction. And then for the data, we need an array of 12 bytes, specifically for the transfer instruction, where the first 4 bytes are used to identify that we're invoking the transfer instruction, which happens to have a value of 2, and the remaining 8 bytes is for the Lamport amount we're trying to transfer. So once we have this data, we're going to split this byte array at the 4th byte and write this data to this array, and then use that as our data in the instruction we're building. So this is functionally equivalent to calling the transfer helper function. The point of this is to say that you can always fall back to manually building an instruction, specifying the program ID, data, and accounts required by the instruction. However, this requires you to know exactly how to construct this data byte array for the instruction you're trying to invoke. Now, if we were to invoke this transaction, we could see that in example 2, we still get back the transaction signature, which we can view on Solana Explorer to see that we've invoked the transfer instruction on the system program. So this here is functionally equivalent to this here. Generally, you would want to use the helper function, but if for whatever reason the instruction you're trying to invoke does not have a helper function, you can always fall back to manually building the instruction yourself, because this is the base type for all instructions on Solana.